Okay. Well, thank you, and I'd be happy to take more questions and do this again if there are other questions. So, but let me go ahead and turn this back over to Kirk and Philip to sort of set up our next panel. Do you have PowerPoints up here?
It's Greenaway.
Oh, okay.
And this is bio over here.
So Louise is going to talk. You're going to talk again? You going to do that first or second?
First.
Okay.
I'm confused.
Yeah, they're going to put both of them in there to talk about seismicity and volcanism. It's two separate. So Louise is going to go first. I don't see Graham's on here. Is his PowerPoint up here?
It's supposed to be on the desktop. It should be. Do you see it on the desktop?
I'm not sure which one it would be. This is hers. Anchorage presentation.
Yeah.
Okay, so that's that one. And she's going to go first, so I'll put this one out. It's there, and then hers is here. Keystone volcanism. Okay.
All right, we're going to start our second session now. The topic is seismicity and volcanism. And Louise Shannon is going to give the first presentation, and then that'll be followed by Graham Greenaway with the second, and they're both with nice Piesel.
It's not showing up. Okay, so originally these presentations were combined, but now they've been separated out into volcanism and seismicity, so I'm just going to be doing the one on volcanism today. So I'm just going to talk a little bit about the regional tectonics of the area, the regional volcanism, and then Graham will be covering the regional seismicity in the next presentation. Again, the information in this presentation is sourced from internal Northern Dynasty and public partnership documents and published information. So, the Pacific tectonic plate is currently subducting underneath the North American plate, roughly 2 to 3 inches per year. And this region is known as the Alaska Aleutian Megathrust. And it's part of the Pacific Ring of Fire, which I'm sure some of you have heard of. So I just put a close-up there showing the Pacific plate going underneath the North American plate, and as you can see, it's pretty much right beside the Aleutian chain. So, and here is just a picture of what's known as the Ring of Fire, which is just all the subduction zones around the Pacific Ocean. And as some background, most volcanoes and earthquakes are associated with subduction zones when thin oceanic crust descends below thicker continental crust, as shown in that diagram as well. How subduction volcanoes form is water in the crust of the subducting plate is released as the temperature and pressure increases with depth. And this water causes partial melting of the mantle and generates magma. This magma rises to the surface of the continental crust and forms a volcano. And volcanoes usually form a linear belt parallel to the trench, which is referred to as a volcanic arc when it occurs on continental crust, or a volcanic island arc when it occurs in oceanic crust. So the magma, which is partially melted mantle, is usually basaltic to andesitic in composition, and the volcanoes generated are generally steep-sided because the magma is rich in silica and it's fairly viscous or quite thick. These types of volcanoes often generate explosive eruptions because the thicker magma does not release gas as easily and causes the pressure to build up. And this is just a picture of Augustine volcano in January 2006, which was the last explosive eruption of this volcano, and it was about 3 months in duration. Took place to March 2006. The mine study area could be affected by active volcanoes that are located near Cook Inlet, and these include Augustine volcano and Mount Iliamna and Mount Redu, and then the other ones are farther away, but they could still have an effect. So as I said, Mount Iliamna and Augustine are the closest to the mine study area, approximately 60 miles away. The last confirmed eruption of Mount Iliamna was 300 years ago, with some possible activity 90 to 140 years ago, but that's not hasn't been substantiated. And Augustine erupted in 2006 and has returned to a typical background non-eruptive state since. And Augustine has generally collapsed and regenerated every 150 to 200 years over the past 2,000 years. So, volcanic eruptions can be predicted by temperature monitoring, gas composition monitoring, seismic monitoring, and visual monitoring for changes in shape on the volcano, and study of past eruptions. The potential hazards of volcanic eruption include volcanic ash or debris coming out of the volcano, landslides or mud flows, also known as lahars, corrosive rain, noxious gas and dust clouds, which are known as nuées ardentes as well, and or tsunamis due to debris avalanches if they occur in the ocean. The regional volcanism hazard for the Pueblo mine study area is volcanoes generally only affect 6 to 12 miles around the volcano, and so the potential for these hazards is considered minor for the mine study area and the Cook Inlet study area. Ash clouds could potentially cause a hazard to aircraft, and there is the potential for some disruption to regular shipping activities in Cook Inlet. And now we'll pass it over to Graham Greenaway to talk about the regional seismicity.
Thank you. Mr. Graham Greenaway has been employed with Knight Piesold since 1991. He has over 20 years of experience in geotechnical engineering and has been a project manager on numerous projects. He has extensive experience in mine waste management and has worked on numerous geotechnical and environmental projects for the mining industry. Mr. Greenaway is also involved in dam safety reviews, inspections, and due diligence reviews, and the analysis and computer modeling of geotechnical problems, including embankment and slope stability analysis, consolidation and settlement predictions, seepage analysis, and foundation design. In particular, he specializes in the seismic hazard analysis, seismic stability and soil liquidification assessments, laboratory testing of soils and mine tailings, and the interpretation of geotechnical site investigation data. Great.
Okay, good afternoon, ladies and gentlemen. I had no idea that I did so much stuff, but thanks for the introduction. I'm just going to load up my presentation. How do you actually get this to view? Sorry?
From the beginning, you had the right thing. Sorry about that.
Oh, okay, good. Okay, as we said, my name is Graham Greenaway. I'm not a geologist. My background is a little different. Probably the best way to characterize myself is a geotechnical earthquake engineer by training, but I do, that's one specialty of mine, but my other area of work and specialty is mine waste management and the design of structures associated with mine waste. So just looking at the presentation outline, what I want to go over with you this afternoon is obviously looking at the seismic hazard for the region, the tectonics and seismicity, but also not just to focus on the bare bone facts of this is the seismicity, this is historically what we've seen. Particularly given my background, I just try to introduce a little bit of the flavor of what that means to us in terms of type of earthquake, the ground motion parameters we derive from that, earthquake characteristics from different seismic sources, and what that means to the seismic hazard at Pebble. One of the discussions that came up a few times this morning is obviously we don't have a project description to be going with the mine plan at this time, but hopefully I can at least give you a sense of how we take this data and move into the next step. So just to summarize, the intent of the EBD in terms of seismicity was to provide a summary of the regional tectonics and seismicity and to provide a comment on the seismic hazard for the Pebble study area. Just going to, before I get too far into seismic hazard, I just wanted to give you basically my understanding of the definition of seismic hazard, which I think is important for when we're looking at this. It's typically defined from consideration of three components. One is the severity, which is measured by the amplitude, the duration, how long the earthquake is, and also dynamic frequency characteristics of the ground shaking, and this is very much dependent on the type of earthquake. The other is spatial, the location of the event relative to the site, obviously it has a big impact, and temporal, how often does it occur? Does it occur frequently, or is it something, an event that occurs, tens of thousands of years as opposed to a few years or decades? Okay, so the seismic hazard that was, in terms of quantifying that for the 2008 EBD, the inputs that were considered for that obviously was a lot of published information that was available at that time. Also very important, the historical seismic data, what earthquakes have occurred and where are they. Another major input was a probabilistic seismic hazard analysis, which is provided by the USGS database. There's a lot of information provided by that on the probabilistic data telling us what sort of ground motion to expect for different return period events, and also the seismic hazard mapping that goes with that. Another component there we considered was deterministic seismic hazard. This is really, once we've defined what potential seismic sources are out there in the region, looking at each of these potential seismic sources or potential generators of an earthquake, and looking at what that impact could be on the Pebble site. We typically look at those sort of worst case scenarios. We call them an MCE event, which is a maximum credible earthquake. Okay, so if we take here just an overview of southern and central Alaska, here we've all the red dots, that shotgun blast of data there is the historical seismicity of the region. Just to bear in mind that this data, the large majority, has probably been collected over the last 50 years, since the early 60s when the International Seismological Society came online and the database was developed. So before that date, only moderate to large earthquakes would have been recorded up until about the beginning of the 20th century, and then a very few very large earthquakes might have been picked up before that. But really, instrumentation for recording earthquakes only really came into being at the end of the 19th century. Also on there, we're showing significant fault structures in southern Alaska to try to start to make some sense of the data we have on there. Now, oops. I want to make sure this is showing up on the screen. Yeah, okay, I'll try and use that. I do have a laser pointer, but it provides a red dot, which isn't very effective. So anyway, what does that show us on there? Well, what we can try to pick out of our knowledge of the seismicity of the area is really have three different types of earthquake. Louise already talked about the megathrust and the subduction zone. So off the southern coast of Alaska, we have, if I can find the cursor and get it to work, this region along here, which is defining the plate boundary between the Pacific and North American plates. So we do have very large potential for very large interface subduction earthquakes, as they're called, along that interface of the two tectonic plates. Also associated with that, we have seismicity within the subducted Pacific plate, which is generated by the stresses and pressures within that subducted slab. And it's not me doing that. Obviously, the third type to consider is shallow crustal earthquakes. There's a lot of stresses, tensions, and pressures going on within the continental crust there with these two plates colliding, and that gives rise to a lot of fault features and shallow crustal seismicity. Some of the well-known ones on there would have been a Denali fault north of Fairbanks there, and then I'm trying to read my screen, but basically probably the ones of note are Castle Mountain fault north of Anchorage. Off the coast we have the Border Ranges fault, Kodiak Island fault, and Bruin Bay fault, and one of note for the project site is the Lake Clark fault. Okay, as I mentioned, there's three different types of earthquake that we can recognize here. One is the interface subduction earthquakes associated with the Alaska-Aleutian megathrust. Two is this in-slab or intraslab subduction earthquake, which is an earthquake occurring within the subducted slab as it's pushing under the continent. And lastly, but not least, the shallow crustal earthquakes associated with active faults. So another way to look at this is through just a schematic cross-section here. If you think of this as showing somewhere with the Pebble Mine study area off to the right-hand side there, we could imagine that island arc there to be Kodiak Island, perhaps Augustine volcano there. Then this gives you a relative indication of where those three types of earthquake are located. We have the large or potential for large. There's also small or moderate earthquakes, but the ones of prime importance for seismic hazard at the site are large earthquakes on that interface of the two tectonic plates. In this area there, I hope you can see that, because I can't, and it keeps moving my slides. So the second type is the in-slab earthquake shown there within the subducted slab, and the third would be the shallow crustal earthquakes within that continental crust. They don't just occur within the continental crust, they are occurring in the offshore region as well and in the oceanic crust or plate, but the ones of most significance for us at the Pebble site are those that would be in the continental crust region. Okay, so let's take our data again and think of another way to look at this. If we look at the distribution of earthquakes by depth, taking that same seismic data, what we've done here is broken up all those red dots, and all those that are greater than 25 miles deep, that's getting below the approximate extent of the crust, is shown in blue. And what we start to see here is a trend where a lot of those earthquakes that were more inshore off the coast as we go north of the coastline are showing up in blue, and that's associated with these deeper earthquakes that are occurring within the subducted slab or associated with that subducted slab. Obviously, we still have a lot of seismicity showing up along the coastline there associated with the megathrust zone where that plate collision is occurring. And there's also shallow earthquakes associated with some of the active fault structures there. The most significant one that stands out is the Denali Fault. And on there we can see where we had the magnitude 7.9 event in 2002. So that, as you start to see from the data, we start to get a sense of the three different types of earthquake that we're dealing with. That each have their own contributions to the seismic hazard at the site. So taking that data a step further now and looking at it in cross-section, what does it show us? If we take a region, as I've shown on that hatch shaded area there, on that cross-section A, if we take all the historical data within that region and plot it up in a 2D section with showing you earthquakes by depth, this is the sort of picture that we start to see. And what that tells us here, it quite clearly shows how you have a lot of seismicity associated with in the crustal areas around the subduction zone, all that interface between the two tectonic plates. You also get a significant amount of seismic data occurring in the subducted slab associated with these intraslab earthquakes. You do get some crustal seismicity in the Cook Inlet area, but basically the level of crustal earthquakes is decreasing as we move further north away from the subduction zone. Okay, so looking at each of these three different types of earthquake in a bit more detail now, starting with the interface subduction earthquakes at that interface of the two plates. What do we know? Well, we can say that, as I've already mentioned, these are earthquakes that are generated by tectonic plates locking and slipping past each other, releasing a lot of built-up energy. These often occur at relatively shallow depths of about 10 to 25 miles. I keep wanting to say kilometers, but it's about 10 to 25 miles, and that's related to the crustal thickness and where that interface between the two plates is occurring. And these do have, obviously, potential for large, or great, as we call them, magnitude 8 plus earthquakes, up to magnitude 9 plus, as was witnessed by the 1964 earthquake, which was a magnitude 9.2 earthquake. These large magnitude earthquakes can last for several minutes. That's an important consideration. Unlike, as you see later, I'll go into a bit more detail on that, but compared to other earthquakes that occur in the crust and in the intraslab zone, the duration of these earthquakes is significantly greater. The estimated period of occurrence of a great earthquake of this type is about 660 years in this region. That's a very general number. I mean, that's an average taken from evidence over the last several thousand years, but approximately about 650 years to get one of these great earthquakes. And as I already mentioned, the most significant of these, a lot of you I'm sure are aware of, was the magnitude 9.2 event in the Prince William Sound region in 1964. And just going back to this map, I just want to make the point that the rupture zone from that, even though we show red dots or blue dots on the plan here, the rupture area for that earthquake actually occurred up in the Prince William Sound region and generated and ruptured all the way down towards Kodiak Island. So it's actually not a point on the map that it's rupturing at. That may be the epicenter, but the rupture area is significantly greater than that. Okay, so moving on to in-slab subduction earthquakes in a bit more detail. These are the ones, as I said, that occur within that subducting slab. Of the three different types of earthquake, these are probably the ones that are least understood, but they certainly do occur and have potential to be large and up to magnitudes in the order of 7 to 7.5 typically. And these are thought to be basically related again to the very high tectonic pressures and stresses occurring within that slab, and maybe even a remobilization of crustal faults that within that slab as it's subducted. What you can notice from this diagram here is obviously these events, because they're dipping down and pushing under the North American plate, they are occurring closer to the study area. So even though they may be of lower magnitude compared to the megathrust zone, they are a consideration because they are close to the study site. So just in summary, what we know about in-slab subduction earthquakes, they occur within the subducting slab. They often occur deep within that slab because now they're occurring at that depth as we're pushing deeper beneath the crust of the continental North American plate. Several moderate to large subduction earthquakes have occurred in the region over the last century. Two of the most notable were magnitude 7 earthquakes, which occurred in 1999 and 2001 in the region of Kodiak Island. Obviously, that tells us there is potential for magnitude 7 events, or 7 to 7.5 type earthquakes of this size in the region in the future. So moving on to the third type, shallow crustal earthquakes, which are going on these crustal faults. Just pointing the blue arrows there to some of the most notable, again, the Denali Fault, the Castle Mountain Fault, and the Kodiak Island Fault. Just wanted to now go through, just explain a little bit about what they are, and then look at some of those faults in a bit more detail, what we know about them. These occur along the active faults in the Earth's crust, and typically at depths of about 25 miles or less. Again, these are occurring within the Earth's crust, so they're only going to be of a limited depth. They're not going to occur deep, like we do with intraslab subduction events. There's numerous fault systems in southern Alaska related to these tectonic pressures and crustal flexure that's caused by the subduction zone, and this does extend quite a way into central Alaska. Before I move on, I just wanted to talk briefly about the definition of active faults and inactive faults. Obviously, active faults, they're easy to define because they're basically ones that do have evidence to show an activity. Inactive faults, a little differently, but typically the conventional definition of what an inactive fault is one that has no evidence of movement or seismic activity within the 10,000 years or more. So, having said that, some faults that have been inactive for 10,000 plus years still may have some potential for activity in the future. Okay, looking at these crustal faults, Denali Fault, I already mentioned the magnitude 7.9 earthquake that occurred on that fault in 2002. This fault does have potential for generating earthquakes of that order up to about magnitude 8, but it is located at its closest distance to the study area for the Pebble site, about 125 miles plus away. So even though it has potential for generating significant earthquake events, it's far enough away that the actual seismic hazard from that wouldn't be considered as high. It would have some contribution, but it's not going to be a high hazard at the site. Similarly, the Castle Mountain Fault, that's certainly had capacity to generate large earthquakes again of magnitude 7 or maybe even slightly higher. The recurrence period for this, studies have indicated, are in the order of about every 700 years, but you could certainly get more moderate earthquakes on a smaller time cycle. But again, this active Castle Mountain Fault, as it's mapped, is too far away from the Pebble study area to cause a significant seismic hazard. And again, in a similar, for the Kodiak Island and now Cape faults, these are both active faults off the coast there, which are capable of generating earthquakes in the order of up to magnitude 7.5, but these are at quite some distance away, I believe about 150 miles plus away from the Pebble study area, so they wouldn't contribute a high seismic hazard. Bruin Bay Fault, this was active in the late Jurassic and again in late Tertiary about 25 million years ago. And some studies have suggested that a magnitude 7.3 associated with this fault occurred in 1943. Again, this is probably of these faults I have listed on this slide. This is the one that's closest to the site. It's about 50, 60 miles away. Again, it would have potential to provide some moderate seismic hazard, but it's not high because it's not that close to the site. Border Ranges Fault is further away, and I think it's considered currently inactive. It has shown evidence of activity in the past of events in the order of magnitude range of about magnitude 7 plus. But that fault in itself is further away than the Bruin Bay Fault. So moving on, probably to the fault of most interest for us here is the Lake Clark Fault. As you can see on the picture there, the Lake Clark Fault is a continuation of the Castle Mountain Fault. It's a westerly extension of the Castle Mountain Fault system. The western end of this Lake Clark Fault, the mapped location of it is about 10 plus miles from the Pebble study area to the east. The main fault and all fault splays may extend further to the southwest, but currently there's no evidence due to a lack of bedrock exposures. There has been some ongoing studies on that. And one thing we have determined from this baseline study is that additional studies are required and are ongoing to examine potential extensions of the Lake Clark Fault. This fault is considered inactive by the conventional definition of 10,000 years or more of inactivity. Recent studies have indicated that there is no activity within the last 10 to 11,000 years or so. Some other previous studies have indicated no movement in the last 1.8 million years. Current evidence does suggest that the seismic risk on the Lake Clark Fault is very low, but I do want to point out, going back to our definition of inactive fault, it doesn't mean that there's anything magical geologically that occurs after 10,000 years. That is just really a definition that's assigned to imply that there's a very low risk associated with that fault because there has been no activity. Just to talk a little bit about ground motion parameters now. These are the sort of the data now that someone like myself would use. What do we get out of the seismic hazard assessment? How do we use this information? Earthquake ground motion characteristics typically defined by the amplitude. That's parameters such as the peak ground acceleration, peak ground velocity, or displacement. The frequency content, often represented by the response spectrum. I don't want to get into the details of that, but it's just a way of representing the types of cycles, whether it's a very impulsive type of earthquake or whether it's a long sine wave type of earthquake. And the third characteristic is duration, which is very important. Obviously, the longer the duration of an earthquake, there's obviously a potential for an increase in damage potential. And these characteristics are dependent on the type of the earthquake, the size, which is typically defined by the magnitude of the earthquake, and obviously the location of the event relative to the mine study area. Here's one very common ground motion parameter that's used in the engineering and design industry. This is the peak ground acceleration. What I've shown here, this is actually a seismic hazard map that's been developed by the USGS for Alaska, and what this shows is the peak ground acceleration for an event with a with a return period of 2,500 years. The significance of this return period of 2,500 years is that's the level that modern building codes use in the design of structures. So the sort of building we're in today would be designed typically, if it's modern design, would be to a 2,500 year return period. What we can see out of this slide here is you can see it when we look at the location of the Pebble project, it tells us that for a 1 in 2,500 year event, the peak ground acceleration is in the order of 0.25 g. So that, and then if you also look at the shading there, that red shading off the coast, it's about 50% of what you might expect in the megathrust region. So what we're seeing here is you have a very high seismic hazard off the coast on that plate boundary, and this decays as you start to move further away from the subduction zone, as you might think. But also some highlight one area there, Denali Fault. You can see there's another red zone, a very high seismic hazard, which was associated with that active fault. This isn't obviously the only return period we consider. We also consider lower and higher return periods in engineering design. Just for reference, the 1 in 10,000 year earthquake would be on the order of about 0.4 g at the Pebble site area, but it would probably be in the order of about double that off the coast. Okay, another way of showing how these three different types of earthquake can be considered is to look at the peak ground acceleration versus distance. So how does that change from the source zone where these earthquakes occur to how they would be felt at the Pebble study area? If you look at our interface earthquake there, that's these great earthquakes that can occur on the megathrust region there. If you had a magnitude 9 interface earthquake, you'd have very high, very strong ground shaking in the source area, but by the time you get to the study area at the Pebble site, it's significantly reduced due to ground motion attenuation. That's just a decay in the seismic energy as it reduces with distance from the source. Now we compare that to these intra-slab subduction events occurring in the subducted slab. That's a lower magnitude event, maybe getting up to magnitude 7, 7.5, but the actual ground shaking experience at the site is higher. Not only because it's closer to the site, it's also because it has, that sort of earthquake has different ground motion attenuation characteristics, and that's something we have to consider when we're developing these design parameters. The third type of earthquake, the shallow crustal earthquake, again, that could be in the order of magnitude 7, 7.5 range. If we were to be looking at a hypothetical event on, say, the Lake Clark Fault, that would also produce higher shaking at the site compared to the subduction events off the southern coast of Alaska. So what I've shown here, I tried to show that there's some similarities between the shallow crustal earthquakes, which would have potential to occur closer to the site, and these intraslab subduction events, which would occur further away, but have different characteristics, so they could have ground shaking that's similar in intensity. Okay, another way of looking at earthquake characteristics is actually look at the waveform. Here we have is what we call an accelegraph. This is just a plot of the acceleration of the earthquake with time, or the measure of the ground shaking with time. These aren't earthquakes that have occurred in Alaska. These are just ones to illustrate a point how these three different types of earthquake that we're looking at can vary quite significantly. We have to consider that in design. The one shown in blue there, that's a shallow crustal earthquake. Actually occurred in California. That was a very near-field earthquake. So as you can see from that, it has a very high peak. I've actually scaled that one to about 0.4, which is about equivalent to the 1 in 10,000 year earthquake, to give a sense of what it might look like. But that was a very high amplitude earthquake. It's a very impulsive earthquake. You can see it does a lot of shaking very quickly, one or two big spikes, and then it's done in about 10, 15 seconds. Shallow crustal earthquakes, they can vary, but typically the strong motion component would be in the order of a few seconds, 10, 20, 30 seconds, maybe a little longer, depending on where it is relative to the site. But in contrast, when you compare that to an interface subduction earthquake, that's what we show, and a good example there is a Mexico City earthquake that's shown in red. This was actually a magnitude 8.5 earthquake, and that's a significantly longer duration. In fact, I've cut off the end of it just for clarity there. If you were to compare this to, say, a magnitude 9 megathrust earthquake off the southern coast of Alaska, that event could go on for, say, 3 to 4 minutes. So it's a very different waveform, a very different sort of earthquake to consider. Putting on the last type of earthquake, this is the in-slab or intraslab subduction earthquake. Again, you can see it's a different sort of characteristic. It's not as long as we have associated with our interface subduction earthquakes, but it's not as short as the shallow crustal type earthquake, or typically is not as short. It can still, as I mentioned earlier, have very high peak ground accelerations associated with it, but is not as long duration as the larger magnitude interface subduction earthquakes. So there, hopefully, just gives you a feel for the three different types of earthquake that we've defined that have contributions to the seismic hazard at the site, and all part of the information that we would consider when looking at design parameters and seismic design of facilities. Okay, so what does this mean to the seismic hazard for the Pebble site? I've already shown you the three different types, but just in summary, the seismic hazard at the Pebble site is influenced by three different types of earthquake. These large or great magnitude earthquakes of magnitude 8, magnitude 9 plus, occurring along the interface subduction zone off the south coast of Alaska. We have these potential for large magnitude in-slab subduction earthquakes, and also the moderate, I'd say moderate as well as large, because if these are closer events, then even a moderate magnitude earthquake can have a significant impact. So it's moderate to large magnitude shallow crustal earthquakes. Again, these large interface subduction earthquakes, just to clarify that, these have a very long duration, but lower ground shaking compared to the in-slab subduction and shallow crustal earthquakes, which would occur closer to the project area. So just to, in summary here, and to wrap things up, ongoing studies that have come out of this, the need is to work to examine hypothetical and potential extensions of the Lake Clark Fault. As I said, it's by definition is an inactive fault, but the Pebble Partnership recognizes the importance of this fault system on the seismic hazard at the site. There is some uncertainty as to how that fault extends to the southwest. There is ongoing work to delineate that fault, and find any more information on whether there's any potential for activity in the future. Two other points to consider. One is an evaluation of potential revisions to maximum earthquake magnitude that's assigned to earthquake sources. I don't see this having a major change in the future, but it is something that's always updated. It is a part of any deterministic or probabilistic seismic hazard assessment to assign maximum magnitudes to potential source zones, and this can change with time as more available information is out there for us to look at that in. So a good example of that is the Castle Mountain Fault passing north of Anchorage, which originally the USGS, I believe, had a characteristic earthquake in the order of 7.5, and that's now been reduced to about 7.1 on average based on more recent information. Another consideration is the impact of new ground motion attenuation equations. That's getting back to those figures, that slide I showed you with the peak ground accelerations decaying with distance. They do change over the years as we get more information. Ground motion attenuation equations for different types of earthquake source do get updated with the new data, and that's something we would consider for ongoing studies. That's everything. Thank you.